All right, excellent. So, have you been able to find the? Okay, you're not looking at the packet. So, unfortunately, we don't have the packet in front of us, which we will endeavor to fix as soon as we can. Otherwise, we're gonna kind of take this time to go over a few different topics and take a look at a sample practice FRQ and maybe talk through a couple interesting questions. So the way that I like to kind of think about this is, let me see if I can get rid of this bar real quick. Hide floating meeting controls. Beautiful. All right. So the way that I like to kind of structure these is for every topic, we're going to sort of think of this the same way. We're going to try to identify some key relationships and equations, figure out when you're supposed to use what. One of the toughest things on the exam, as you may have found during the practice mechanics exam, is that when you're looking at a question, you never quite are sure whether this is going to be a kinematics question or a forces question or what, right? So what are the clues that you can look for? No, it's not video, it's the audio. That's yeah. What are the clues we're looking for to find out what kind of approach we should be taking? And then thinking a little bit about some of the stuff we may have forgotten from all the way back there. So we'll go through some key equations, a couple sample multiple choice questions. Ideally, we would give you some time to work on your packet, but unfortunately, the packets are still at the printer. And then we have a little practice FRQ, which is going to cover some of the things that we have been looking at in forces and kinematics, and give us an opportunity to kind of look at what they're going to ask us to do on the exam and kind of reorient towards maybe more exam focus. All right, so coming back to kinematics, right? The basic idea of kinematics that we want to try to remember is sort of this relationship between position or displacement, velocity, and acceleration. And I sort of like to visualize it as being a little bit of a ladder, right? That if you are going down that ladder, you're taking derivatives or you're finding slopes, right? Depending on whether you have a graph or you have an equation. If you're climbing back up that ladder, you are typically taking integrals, you're typically finding areas under graphs. It is possible. There are derivatives below acceleration. They rarely ask you about them on the exam, and if they do ask you about them, they will always define them. If they want you to talk about the jerk, they will be like the jerk, which is the derivative of acceleration or the third derivative of position or whatever. They will always be very specific about what they want there. That's kind of in general, and you're going to put on your calculus hat anytime you see calculus stuff, right? So if they are like, anytime you see something that looks like an escape from BC calculus, if they're like, a toy car has a position given by 3t squared minus 9t or whatever, if it looks like it escaped from AP calculus class, do calculus to it, right? Like if it looks like a BC calculus problem, it probably is. It probably is. Excellent. Would it be the worst if I asked you to take your conversation down? I'm sorry. Like we're recording for posting, and I don't want to have like side conversations in the background of the. No, how's it going? We're doing an AP review session. I'm gonna ask you to do that in another room though, because we're recording something. Sorry. It's okay. All right, great. Sorry. So if it looks like a calculus problem, it probably is a calculus problem. The other set of kinematics things we often get are the other set of calculus of kinematics things we get are kind of where we use our kinematics equations. And remember, that's only true if our acceleration is totally constant, right? If your acceleration is constant, you can use your good old algebraic equations. If your acceleration is changing or they give you complicated functions of time, you've got to do calculus things to it, right? They give you all of the equations you need on the sheet. There is one secret sort of fourth kinematics equation, which is that if you've got, again, perfect acceleration, then your average velocity is actually, wow, this is really slow. Your average velocity is just the average of your initial and final velocities. That doesn't come up all the time, and in fact is not needed for the exam, but it's one of those things that's really can be helpful to have in your pocket. It can save you time. The key thing to remember, by the way, on this, these three equations do three different things. The first one sort of relates velocity and time. The second one sort of relates position and time. And the third one I like to think of as relating velocity and position. The third one doesn't have time in it, right? So it can be very handy for problems where finding the time is awkward or annoying. So that's kind of generally the case. The one wrinkle we often have is 2D motion, where typically X and Y are pretty separate. And the important thing to remember is you're always keeping them separated, right? If you're doing X calculations, they're only using X quantities, X velocity, X acceleration, whatever. If you're doing Y motion, it's only Y quantities that are allowed in the equation. The only thing that kind of falls in both camps is time. You will have to do some projectile motion. It's like one of the most popular topics on the exam. And remember, for projectile motion, the key thing here is there's no X acceleration. Your X velocity is perfectly constant. And that means in the X direction, it's really boring. It's just speed times time. In the X direction, the Y direction is where all of the action happens. And the most critical thing to remember is that the Y velocity is 0 right at the top. So that's a really helpful way to find times up and times back down. So like, you can use your first kinematics equation, right, to find the time coming up. You can use 1/2 AT squared to figure out, if you know the height, how long it falls. So there's a variety of different equations you can derive here. You might remember, if something drops at one point, you might have remembered that the time for something to drop is root 2h over g. That was a thing that, like, in September, people were writing down on their warm-ups all the time because it was just like a thing that you had in your heart at that point. So projectile motion is pretty clutch. How do you know when to do kinematics? The number one clue for knowing you need to do kinematics is kinematics loves time. It's obsessed with how long things take, right? It's like, how long does this take? Where is this going? Especially in relation to distance, velocity, or acceleration. Any kind of projectile motion or free fall, if it's launched or dropped or thrown, is probably kinematics. If they don't give you mass, or the mass is not needed, that's also a clue. Or they give you acceleration or velocity explicitly. So like, here are some past FRQs where, like, for this one, they launched a little dart that hit a box. So you're going to do kinematics in the front half as it's flying through the air. And then, well, when it hits the box, what are you going to do then? Then you're going to do some momentum stuff, right? This one's an old rotation question where they have like a cylinder rolling down the ramp. So you have to do a bunch of rotation stuff. And then it falls off the table. And then the back half of the problem is projectile motion, right? They love to do these questions where some stuff happens and then there's kinematics at the end. This is one that from a couple years ago where they give you the position as a function of time, and then they ask you to determine the speed, and you should be like, aha, well, I need to take a derivative here. So kinematics, really, you're going to be looking for projectile motion. You're going to be looking for those explicit cues of where is it, when is it, how fast. And it typically is obsessed with time. I picked a few projectile motion questions, which I believe are also on the packet, but of course you don't have the packet in front of you. So we're just going to talk through them and kind of think about them together. So we got a target. This is very wordy, but this is a classic one. We got a target lying flat on the ground. We're going to roll a ball off the roof. Air resistance is negligible. And how fast does it have to be going? So I guess when we think about this, there's like a really important missing piece of information here that we need to find. What do we think we need to know? Well, let's kind of back up. What do we know? Sometimes with kinematics, it's helpful to start with what do we know? We know the distance in the
height and from the edge.
Right. So we know we know kind of, y final is 0. y initial is 10 meters. We also know kind of the delta x here is 3 meters. Do we know anything about the initial velocity?
No, that's what we're solving.
Well, yes and no. We know the
Initial line loss.
yeah, we know that the initial velocity. We don't know v0x. That's what we want to find, but we do know that the initial y velocity is 0. That's a really good one. Okay, it wants the horizontal speed, so we might want to start in the x direction. We also know that there's no acceleration in the x direction. So we might look at our second kinematics equation and be like, delta x is going to be, well, there's no 1/2 at squared. So it should just be v0x times t. Well, I want to know this, and I know that, which suggests to me I probably need to find time. Where am I going to look for time?
The y direction.
Yeah, y direction, because it's falling. We need to know when it hits the ground. Which kinematics equation am I going to grab for that?
Second.
Yeah, the second one's really good because we have two positions and initial velocity. We do know the acceleration, which would be g, and we're looking for a time. So if we set that up, we can go y final is 0, y initial is 10, minus 1/2, gt squared. There's no initial velocity, so I don't need that. If I go ahead and just take g to be 10, which you can do all over the exam, and I would advise you to, you can get t equals √2, which then tells me that my x velocity needs to be what? 3 over √2, absolutely. Because we need to find our x velocity, we're going to need to go delta x over t, right? It goes 3 meters. It takes √2 seconds to do so. So sometimes you need to kind of work around a little bit and figure out which directions you're looking at. Cool. Here's one. I'll blow up this graph for you so you can take a moment. So let's try to figure out, it asks us, here's the velocity. At which time of the following times does its acceleration have the smallest magnitude?
Reads it 5.
I just see.
Oh,
Yeah, 4 seconds.
yeah, 4. Yeah.
All right, at 4 seconds, what's our acceleration?
0.
0, right? It's nice and flat. It's also, if you put your calculus hat on, the velocity is a maximum. And we know that at maxima, the derivative has to be 0. So right here at this point, we get a 0 acceleration. You do want to be a little careful because it might be asking you something different. In this case, it is asking you for that. But if it was asking you about, like, I don't know, basically you're going to get a positive acceleration here and a negative acceleration there. Different parts of this graph could be showing you different things. How would I figure out how far the elevator goes?
Area.
All right, how would I find the area? Because I don't actually know what that function is. I can't put it in my calculator in Math 9 yet.
Try to just
So
count.
literally count boxes. So take a moment. And if you want to come up to the screen, you're not going to ruin the recording, but take a moment and see if you can count how many boxes there are.
14, 16.
Like 15.
Okay. Yeah, I think those are all pretty reasonable. I kind of cut it in half. It's pretty symmetrical. So this is like 3, 2. These two together mostly make 1. These two together mostly make 1, and then these two together mostly make 1. So I get 3, 4, 5, 6, 7, 8 per side. So I'd say something in the realm of about 16 meters would be good. But yeah, finding the area under the graph. So sometimes the function. Sometimes they literally want you to count boxes. And if there's no other way for you to find the area, just count the boxes out. All right. Very nice. These are, by the way, all real questions. So take a moment here. Here we've got a velocity versus time graph. If you want to channel your inner Miss Shrek, it's a good strategy on the exam. Literally, anytime they show you a graph, the very first thing you should check is what the heck they're graphing, because knowing what they're graphing is going to guide what you're going to do. So take a moment. If that's our velocity graph, which is our position graph.
Okay.
Okay. Why would you say A?
Because in the middle, the V is 0, which means that you have like the value of 0, and that eliminates C and B.
Yeah, so absolutely. So it's good to look at features. So you're right. You should have a 0 velocity. And if you're looking for a 0 velocity, what should that do to the graph?
Flat.
It should be flat, right? You're taking an integral effectively. You're undoing a derivative. So it should be flat in the middle. And actually okay, technically B is also flat in the middle. But it cuts out literally all the other ones. How do I feel about B versus A? Why might I prefer one to the other?
A is increasing while velocity is positive, and B is at 0.
Very nice. So all over here, our velocity is positive. So our position should be increasing, and then our position stops increasing. And then our velocity is negative, so we start going back towards 0. You'll notice if you sort of think about taking the integral of this, your total displacement should be 0. You end up back where you started. So I would definitely agree that A looks pretty good. And so again, this is a place where putting our calculus hat on can be very handy. This is one I put on here because it falls into an interesting realm of question that, so I want you to think about this for a moment. In order for the object to travel a maximum horizontal distance, what angle should we throw it at? And notice, if you look at the choices, there's a choice here that is not there. What choice is very notably not given to us? Well, horizontal would be 0. Yeah. What answer is sort of very
Less than 0.
well? Yeah, that's true. I guess if you're throwing something from flat ground, the optimum angle is 45 degrees. If you're up on a cliff, 45 degrees is not the optimum angle. So I want you to take a moment and think about this, and see if you can figure out what the answer is. All right. I guess, why do you want to, like, what does throwing something at an angle get you? Like, if you want to maximize your distance, right? If you want to maximize your distance,
I don't move the
yeah, it's x velocity times time, right? So if you raise your angle, right? If you make your angle bigger, what is that? How is that good? What does making your angle bigger get you?
More time.
Gets you more time because it increases your y velocity, your initial y velocity, which gets you more time. But the downside is if you increase your angle, what else happens?
It increases your horizontal velocity.
It decreases your x velocity, right? Conversely, if you lower your angle, you get less time, but your x velocity goes up. Is there anything you think we can probably eliminate here?
Below the horizontal.
Okay, well, below the horizontal, oh yeah, okay. Greater than 0, but less than 45. Okay, below the horizontal is going to hurt you in 2 ways. It's going to make your time go down, right? Because you're now throwing it down with the ground. So I agree that E is probably up. Yeah, I agree with A because notice it doesn't give an upper bound. So greater than 60 degrees includes what? Like, make it ridiculous.
Backwards.
Right? If you throw it straight up or backwards, that's probably not great, right? So the real question is, being on a cliff, do you want it to be a little bit more than 45 or a little less than 45? You want it to be a little less than 45. I've realized I've just given a bunch of questions, all of which were the answer was C. It's important. C is one of the answers on the test, by the way. So yeah. This one is a little hard to visualize sometimes. You can pull it up in Desmos. The way that I like to think of it is, imagine yourself on a really huge cliff, right? You don't want to throw it down or whatever, but if you're on a really huge cliff, like, how much extra time are you getting from firing the thing upward? Like,
Not much.
not much at all, right? You don't want to shoot it downward, but the higher your cliff is, the more x velocity you want. So it's 45, the optimum angle is 45 degrees on the ground, and the higher you get, the flatter you want to throw it. So in any case, one of those intuitive things that we don't really talk about that much because it's an annoying optimization problem, but it is a thing you can do. Here's one last one, which comes up every so often and tends to give people fits. So we've got a particle moving, and they're going to, rather than projectile motion, it's 2D motion, but they're going to straight up give you the x and y coordinates. This is a thing we do in multi. It's a thing we do in BC. I know with parametrics. How would I find, if I've got the x position and y position, how could I find the speed? Yeah.
Yeah, take the derivative of both and use the Pythagorean theorem.
Yeah, so I could do x prime here, right? Which is, you can think about that as being the x component of the velocity. So I get like negative 15 sine 3t. My y prime, which would be my y velocity, would be 15 cosine 3t. And it's very tempting here. I'm going to play the part of the very tempting person, be like, aha, sine and cosine. I'm going to be like, oh, it oscillates, right? It oscillates. Well, I forgot to do what Zion said, which is I forgot to do the Pythagorean theorem. And if I do the Pythagorean theorem to find the magnitude of my total speed and the magnitude of my total velocity, I get 15 squared times sine squared of a thing plus 15 squared times cosine squared of a thing. And one of the things that we know about sine squared plus cosine squared is you always get 1, right? So this is just 15. So the things just go in a circle at a constant speed of 15. It's just going in a circle at a constant speed of 15. So just be a little cautious with those things. All right. Normally, and again, just be confident with your kinematics equations. Think about what you know and what you want and use that to pick your kinematics equation. And that you just got to be careful if you think it's a kinematics question, is your acceleration constant? If so, go for the equations. If your acceleration is changing, you need to use some calculus. All right, we're going to do a little forces, and then we're going to talk about this little practice FRQ guy here. So the most important thing with forces is drawing free body diagrams. I guarantee you will have to draw. Okay, I guarantee you one of the FRQs will give you 3 or 4 points for drawing a free body diagram. And many of the multiple choice questions, you should be sketching yourself. Oh, this thing's going down a ramp. I'm going to sketch myself a little free body diagram on the side of my paper. You should be drawing free body diagrams. So quick recap, of course, remember your Newton's laws, right? I would say the Newton's law that people forget the most is the third one. For whatever reason, people really don't like to believe that when a giant asteroid hits a tiny fly, that the force that the fly feels and the force that the asteroid feels are the same. The fly is affected a lot more, but it is
Higher acceleration.
Yeah, higher acceleration. You can think of it as F equals ma, right? Little mass, high acceleration versus big mass, little acceleration, but the force is going to be equal and opposite. So make sure you know that. Remember all your forces, gravity and tension. Be careful with friction. Is it static or is it kinetic? Because they operate differently. Quick, not a cheat, but a quick hack. If you're drawing a free body diagram and you know that there's friction, but you don't remember whether it's kinetic or static, what should you label your vector as? Yeah, just label it as FF or F friction and then work it out later. Because if you commit to being FS or FK before you figure it out, if you commit, you'll be in little trouble. Springs, all of those things should be on there. Remember centripetal force, right? The acceleration is v squared over r. Anytime you see something going in a circle, even if you like slightly suspect that circular motion is involved, you need that net force towards the center of mv squared over r, right? It can be multiple forces. It can be like gravity and tension fighting, but you need a net force towards the center that is mv squared over r. By the way, they do give you the, like if you're doing angular stuff, you can also write it as omega squared times r. So if you're doing a rotation problem and omega is easier, you've got that. Drawing your free body diagrams, You draw your free body diagram, pick your directions of motion, right? So like, is it X versus Y? Is it horizontal? If you're on a ramp, maybe your directions are going to be down the ramp and perpendicular to the ramp. And then you're going to write out Newton's second law in those directions. You can always derive these things. You've got your formula sheet, but the more things that you can kind of just pull out of your pocket. So if you've got a thing on a ramp, remember sine for slide, right? The parallel component of gravity is usually sine, unless they are being mean to you and they give you this as the angle, in which case they're opposite. But usually they're not trying to be too mean to you, right? If the ramp looks nice and normal, sine for slide. The sine component is the one down the ramp and the cosine is the other one. For pulleys, remember the one way to think about this is that the pulleys sort of bend your coordinate system, that if, this mass is moving down, other things might be moving up on the other side. And for the moment, we'll come back to this when we talk about rotation, we usually assume that the tension on both sides of the rope is the same. That's only true if everything is nice and ideal. If your pulley has mass, that stops being true, but for most cases, the tension is the same on either end. Again, you probably are pretty good at drawing free body diagrams at this point, but if you forget what you're doing, you can always go back to that AIDA method, right? What are all the agents acting on my object? Oh, I've got a rope, I've got the earth, I've got this ramp. And what forces do they apply? What interactions do they have? Okay, the rope's going to apply a tension force, earth's going to apply gravity, and the ramp gets friction and a normal force, right? So this can really help you in weird situations if you don't know how many vectors to draw. And if you can't identify an agent for it, it doesn't get a vector, right? It doesn't get a vector. And we might actually see that on our FRQ in a moment. Sometimes they will give you a grid and ask you to draw your vectors like relative to the grid. You just make sure that if one vector is bigger than the other, you give it 3 boxes instead of 2 boxes or whatever, right? So make sure that. Maybe the biggest rule is they want you to draw vectors, not components. If you are drawing a car on a ramp and there's no friction or whatever, they want you to draw mg down, normal force that way. Stop. Now, of course, you might need to split that normal force or split these forces into components. What you're going to do is, this is your answer to the question. And then off on the side, you can sketch yourself the little components of it to work that out. They don't want to see the components on the actual free body diagram, though, and they will usually very explicitly state forces, not components. So just be clear about that. Cool. There is a special case that you probably forgot about that they occasionally want you to prove, which is linear drag. So we're going to take a moment and we're going to remember how to do linear drag. So we're going to make this assumption. We're going to take an object and we're just going to release it from rest. We're going to start it at a velocity of 0 and we're going to drop it. And as it falls, it experiences this drag force that we'll call negative kV, where k is some constant and v is the speed. So as it gets going faster and faster, it gets more and more drag force. And you might remember from our coffee filters or other things, if I wait long enough after I've dropped this, what happens to its speed? Yeah, it reaches terminal velocity, right? Because if it goes fast enough, then those two forces will be balanced and it'll stop accelerating. And you can, in fact, find that terminal velocity by setting these two forces equal. And your terminal velocity will just be mg over k. So I just want to solve this because every once in a blue moon, they will be like, do the calculus. So let's think about this from a forces perspective, right? If we take down to be our positive direction, we're going to go ahead and get mg minus kv equals ma. If I'm looking for my acceleration here, that will be g minus k over m times v. And here's where it's important to remember that what is acceleration with respect to velocity? What's the relationship between acceleration and velocity? Derivative, right? That acceleration is the derivative of velocity. So we get a differential equation, which is just an equation that has derivatives in it, that tells you, hey, the velocity function you're looking for is related to its own derivative in this peculiar way. So we're going to try to solve this. They will occasionally give you differential equations, and they will always either be simple harmonic motion ones or they will be separable. And by separable, what that means is we can get all of our t's and all of our v's on opposite sides. So what I'm going to do is I'm going to put all of my v stuff over here. And I'm going to put all of my t stuff over here. And what we're going to do is we're going to integrate these. Now, there's a couple different ways to integrate them. You can integrate them with like a plus c variable. In here, we're going to go ahead and integrate these a different way. Our time is going to go, we're going to go from 0 to some later time t, right? If I were being responsible, I would use a dummy variable. And then our velocity started out at 0, and then later we'll be at some speed v, right? At some speed v. So we're gonna go ahead and integrate both sides. My right side, well, I think turns out to be pretty easy. What is the integral dt from 0 to t? I get t on my right side. Now my left side looks a little funky, but if you squint, we have a dv on top and some stuff related to v on the bottom. Like if you imagine looking at an integral that was like 1 over x dx, right? That's an integral everybody knows. That is the natural log. That is ln of things. So we're gonna do a thing that might give other calculus teachers some bother. We're gonna sort of eyeball the chain rule here. So what we're gonna do is we're gonna be like, well, that looks like maybe an ln g minus k over m v. I actually should be a little careful on this side. Let me not be too hasty in this case. Now that's not quite right, because you'll notice if I do that, you can always check an integral by taking a derivative. If I take a derivative of that, I do get 1 over this, but what would I chain out if I take that derivative?
K over M.
I get a negative k over m out. So I'm going to kind of preload to cancel that out. I'm going to put a negative m over k. And that way, when I do my chain rule, they will cancel each other out. Now, I was muttering to myself about being careful. I should probably actually do this from 0 to v, like I said I would. So what I'm going to get is I'm going to get negative m over k ln of g minus k over mv. And then minus, if I plug in v equals 0, I just get
Log M over K, log natural is 0.
of g.
Can you combine those?
I can combine these. I can combine these. Let me be a little careful about combining them. I'm going to end up with that being a plus. So if I factor out in m over k, I get the natural log of g minus the natural log of all this goodness. And one of the... Okay. I didn't do something wrong, but I made my life harder for no reason. For reasons that will become clear in a moment, we are going to keep this minus sign out here. There's a reason, by the way, that I usually like to do it the other way. But that's we made a plan and we're gonna commit to it. Minus ln of g equals t. If I have a difference of 2 ln's, what does that do?
It's like the ln of the ratio.
The ln of the ratio, right? So what I'm going to get on my left side, and I'm going to deal with this. I'm going to punt this m over k to the other side. And what I'm going to get here is I'm going to get the ln of 1 minus kv. Oops, that's the worst k I've ever written in my life. Kv over mg. And now I'm almost there. I'm going to go ahead and do e to both sides. So I get 1 minus kv over mg equals e to the negative kt over m. And then if I do a little bit of algebra, I want to solve for v here. I'm going to kick that over to the other side. So I'm going to get kv over mg equals 1 minus e to the negative kt over m. And at long last, I'm going to get my actual function for my velocity, v of t, is going to be mg over k times 1 minus e to the negative kt over m. That mg over k, by the way, is our terminal velocity. So this actually reads as our terminal velocity times 1 minus e to the negative kt over m. And the way that this graph looks is that over time, and it's really important, actually, the derivation comes up sometimes, the graph comes up a lot, is that whatever your terminal velocity is, your velocity is going to start out at 0 and asymptotically approach your terminal velocity.
That density in the bodega will be closing in about 35 minutes. So this is the last call for the bodega taking place in the cafeteria. Please make your way down if you haven't already to receive your goods. Thank you.
Minus e, but I see that you moved the negative.
Yeah, I moved around.
How did the 1 minus happen?
So what happened is I kind of added the kv over mg to this side and then subtracted the, or how did this 1 minus happen?
Yes.
Oh, okay. So when I did this thing, when I combined these, I kind of divided everything by g.
Okay.
I kind of divided everything by g. So the shape of the graph is really important to know. And we're actually gonna see that exact graph again next week in an electronics context, which is fun. Just being careful about drag. How do you know when it's forces? Again, if they ask you to draw a free body diagram, it's pretty clear what you have to do. If there's friction, it's probably a forces question. Maybe it's an energy question, but probably a forces question at least. Inclined planes or springs, pulleys or tension, any kind of circular motion, right? So if a thing is being whirled around in a string, you've got a pendulum, there's going to be some centripetal forces. Anytime you have statics, if the object is like held in place, it's probably some kind of forces question. And one key phrase to look out for is constant velocity or constant speed. The moment you read those, you should underline that on your test, because the moment you see constant velocity or constant speed, what do you know? Yeah, the net force is 0. There's no acceleration. So a really good thing to look out. All right, cool. We're going to go ahead and take a look at some things, and then we'll look at our FRQ. So here, again, these are real past multiple choice questions. So we got a 5 kilogram object, and we're given a force in newtons that is F equals 0.5 times t, and we want to know its speed at t equals 4. Hey, look, we've got a function that's got a t in it. It kind of looks like it escaped from math class. So we should treat it as though it escaped from math class, right? We have a force. We want a speed. What's the kind of missing? There's a missing link in here somewhere.
Okay.
Yeah, we want to go ahead and find the acceleration. We're told F equals 0.5 t, but we also know that the net force is going to be ma, 5 kilograms times a. So our acceleration here should be 1/10, I guess, 1/2, yeah. Should be like t over 10. What would I do with that acceleration?
Integrate it.
I would integrate it, right? I can't use kinematics because it's not a constant acceleration. So I would then have to integrate that from 0 to 4. It's worth noting you have access to Desmos the whole time. So you can do these by hand. There's, especially in the multiple choice, if you figured out the integral, just put it in Desmos. You know, you can check it by hand if you get a weird answer, but it's always good to do. So that would be t squared over 20. T squared over 20 from 0 to 4, so that'd be 16 over 20, which is 4/5. No. Yes. Yes. 4/5. I can, yeah, so. Hey, it's not C this time. Not C this time. So, and if I wanted to, what if I wanted to know how far the object moves in that time?
Or integral.
More integrals. More integral. More integral. Okay. Oh, this is one of I picked this one a long time ago because this is one of those pocket things to know. Does anybody remember that relationship with friction if it's in equilibrium?
Tangent.
Mu equals, yeah, tan theta. By the way, that works in two different ways. So if you're talking about static friction, that's the critical angle where it's just not slipping. It's the last angle where it slips. If it's kinetic friction, as it is in this case, it's the angle at which you will slide down at a constant speed. Slide down at a constant speed. So it is still mu equals tan of the angle. That is a thing to be on the lookout for, because it's one of those things they might just drop on you. And you can work it out with a free body diagram, but like they're more generous with time now than they used to be. Now they give you 40 multiple choices in 80 minutes. It used to be 35 multiple choices, so fewer in 45 minutes. Like it used to be go, 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 go. They've almost doubled the amount of time per question. But it's still timed. And so some of the questions are 5-second questions and some of them are 5-minute questions. And the more that if you can snap off the 5-second questions, then it gives you just more time to sit and ponder the really thorny. Cool. A lot of words. They love words.
No.
Lynn doesn't love words, but the AP exam loves words. Okay. The accelerations of the directions of the acceleration vectors. All right. Okay. Let's try position R first. Which way is my ball accelerating at position R? Oh, well, those are different options. Okay. Oh, okay. What are the forces on it at R? Gravity and tension. Now it's moving in a circle. Excuse me, which suggests that maybe the radial component of it should probably be what? You see a circle on the board. Now here's the thing. How fast is it going at point R?
Zero.
Yeah, it's not moving. So the tension would be nothing. So the only acceleration is mg, which is down. All right. So at point R, it's accelerating downward, which leaves us two options about where it's accelerating at point Q. Help me out. What forces are on it at point Q? Tension and gravity. I know one of those needs to be stronger because my choices are upwards or downwards. Which force should be stronger? Yeah. Why should the tension be stronger? It's moving in a circle, right? It's got to have that, the net force in that vertical direction, right? T minus mg needs to be mv squared over r, right? It's got to have a little extra tension to pull it up into the circle, or else it's not going to do that. So at position Q, it needs to be accelerating towards the center of the circle. Very good. Centripetal forces. Okay, help me draw a free body diagram for block. Has anybody ever gone on one of these at the carnival? They're slightly nauseating, but really fun.
Yes, they're fun.
We should take a field trip and smuggle a tennis ball in and throw it across the.
You just need a bunch of.
Oh, actually, speaking of which, after this, I should show you. To the physics teachers, I should show you. I was watching some stuff about about Artemis 2, and they had a picture of Artemis 2's orbit in the way you normally see it, which is the Earth-Moon frame, where it like goes and makes a nice circle of the Earth. But I also saw an animation of it in the Sun frame, where the whole system is moving, and it really just like whoop, like it basically like blips by the moon, and just like a little as the moon leaves it behind. It's cool. All right, I need a free body diagram for this.
True.
What you go on it?
Gravity.
Gravity. What else?
Friction.
Friction. Which way is friction pointing?
Up.
If it's staying still, I want this to be. It even says.
Static.
All right, and then I got Normal force pointing inward. What else I got? Trick question. There's nothing else.
Yeah.
How do I know there's nothing else? All right.
Nothing else.
Well, there's the Earth providing gravity, right? What else is what's touching the block?
The wall.
The wall. And surfaces can only provide two forces. They can provide an Fn and they can provide friction. It's not touching anything else. There's no other agents. It can only have three vectors. So in this case, I know, what do I know about my forces?
The force normal's radial. It's mv squared over r.
Yeah, my normal force is going to be mv squared over. Now in this case, they've given us omega, so I'm actually going to write it as m omega squared times r. That's on your formula sheet. So that's my normal force. What do I know about my friction force? Yeah, it's equal to gravity, right? Now the thing is, static friction is a slippery beast, right? Static friction can be less than or equal to mu times the normal force, right? Can be less than or equal to mu times the normal force. But I want my static friction to be equal to gravity. And my mu times the normal force is going to be mu times m omega squared r, which means now I can do some cancellation. And I end up with mu has to be greater than or equal to g over this stuff. Oops, I put a mu on both sides because I'm not paying attention. I'm a wise guy. So so we can go ahead and solve for this one, and it is B. So just be careful. Sometimes you get unusual free body diagrams. Drag. Hooray! Hey, it's running out of gas. Hey, remember how we talked about that resistive force? So we're gonna get that kind of drag looking graph. What pair of graphs best represents the speed and position of the car? First graphs are the speed graphs if you can't read those. So these are the V graphs. These are the position graphs.
We just find the speed graph earlier.
Which ones look like the right speed graphs?
B and C.
Yeah. Well, so it's a little bit unusual because here, what would we assume that the final, like the terminal velocity of our car would be? 0. So it should asymptotically approach whatever the final velocity is. So this one is not an asymptote, it just gets 0, right? This one is nice and curvy, but also just bonks into 0. So the only ones that asymptotically approach stopping are B and D. How do I know which X graph goes along with it?
D, because the axis seems like it's moving backwards.
Yeah.
It's like the distance should be increased.
Yeah, so the relationship, right, is your velocity graph should be the derivative of your position graph. And as was, I think Leo was saying earlier on one of the other graphs, right? Notice our velocity is decreasing, but our velocity is always positive. And if our velocity is always positive, our displacement should be always increasing. It should like peter out and gradually approach being stopped, right? So it is in fact. All right. We're going to take a look at our FRQ here. This is a real FRQ from 2006 when I was alive. So I don't want you to do the whole thing because this is the old style, whereas it should be about 15 minutes. I really just want you to take a few minutes. I'm going to pause the video so people watching it don't have to sit here for 7 minutes listening to silence. And I want you to just give your first impressions. Sketch the free body diagram. And then, like, you can talk amongst yourselves if you want. How would you approach this? Like, what, with the caveat, of course, we're reviewing forces and kinematics. Like, what kinds of equation? Like, write down the equations you're thinking of. Write down what you think your overall approach would be. So, we're gonna put 7 minutes on here, and I will see those of you watching the video in a part B. All right. Welcome back. To those of you who are joining us online. So I do want to note, by the way, this is an older FRQ from 2006. And so it tends to be very calculate heavy. If you were seeing this FRQ on your exam in May, it would probably have half as much calculate and more like if I increase the mass of the slab, what would happen to this thing? So more check and explain and justify, which depending on your attitude is either easier or harder, depending on your proclivity. So let's go ahead and take a look at this. We have a small block placed on a long slab, and then initially the slab is at rest and the block mysteriously has some initial speed to the right. And we're told about the coefficient of kinetic friction. So let's actually start with the slab. Let's start with our slab buddy. What forces are going to be on our slab? Gravity on the slab, right? How should I label gravity on the slab?
Gravity's MS.
Yeah.
MSG.
No MSG in this. Yeah. MSG. All right. What else goes on my slab?
The other gravity.
Normal force.
The normal force from the.
Ground.
Yes, to both of those. So I do need a normal force from the ground. I'm going to go ahead and call that Fn. I could call it FNS if I really wanted. And what else am I going to have on the slab?
The block.
I'm going to have the block. I'm going to go ahead and call this FB. You could call it actually. I'm going to call it
FNB.
FB on S. The force of the block on the slab. We'll find out more about that later. There's one more force though that I need for my slab. Yeah, friction pointing
to the.
Yeah, because if you think about what's going to happen, the block is sort of going to push the slab to the right, and the thing that's going to be doing that is going to be kinetic friction. They do in fact tell you it's kinetic in the problem. There is no friction with the surface. If I go back to my block, let's start with the easy ones, and then we'll talk about the problem. What should I find on my block? Gravity, MBG. I'm just going to be careful here. I don't want to reuse labels unless I want to be careful with my labeling. What other forces should go on my block? The normal force. And here, I'm going to go ahead and call this F. S on B. I want to be careful not to call it Fn. If I did call it Fn, I'd want to call them two different Fns. You don't want to use the same label in two places unless they are like literally the same force. Yeah.
Could I say FNS for the slab?
FNS and FNB would be fine. Or yeah, you just the only time you want to put two vectors on two different free body diagrams and like label them the same is if you are really deeply confident that they are the same force or have the same exact magnitude. Otherwise, you can get yourself in. Yeah. There's one more force on the block, which is friction pointing to the left. Now, the one that tends to get people is people really want to draw a force that way. It's so tempting because like, oh, it's going. So it's something. It got thrown. This is where we go back to what's the agent? What is it touching that's pushing it to the right? And the answer is nothing. We don't know why it has this initial velocity. Maybe it was launched out of a cannon and hit. That force, whatever launched it in the past, is in the past. We're talking about this moment. It has a velocity to the right, but it's slowing down. Furthermore, if you do put in that force to the right, it becomes very difficult / impossible to solve the rest of the problem. So that's what we should get. 4 vectors for the slab and 3 vectors for the block. Let's kind of go through the rubric so that you can get an idea of how they would be scoring this. So this was a 4-point question back in 2006. For the block force diagram, let me try to make this a little bit bigger so people who are actually in the classroom can see this. For the block force diagram, you get basically a point for the horizontal force, which is just friction to the left, no other forces or vectors. And then a point for correctly labeled vertical forces, normal up and weight down, gravity alone not accepted. So you need both vectors. It's basically a point for horizontal forces, a point for vertical forces. For the slab force diagram, a point for correctly labeled horizontal force and a point for correctly labeled vertical forces. They were in fact fine with you drawing one vector down if you somehow indicated that it was the combined weight of the two objects. But I think it's safer just to draw 2 vectors and move on. Yeah.
I'm just wondering, is it fine for on the slab? When you're having the weight of the block on the slab, would it be okay to write that as the normal force on the block? Or would you have to say it's specifically like the mg or weight?
Oh, like for this one, for that?
Yeah.
You can write it either way. I I personally think it is a better idea, and this is a stylistic thing rather than it being a right or wrong. I like labeling it as the force of B on S because that lets me see like a Newton's third law pair. I've got S on B, B on S. Those are going to be exactly equal and opposite. It is the case in this case, because the block has a boring free body diagram and these two things are the only forces, it is the case that this force is just going to be MBG, but like, I think sometimes there's places to cut corners and be very confident. And, you know, if there were other weird things going on in this diagram, like, I don't know, if somebody's pushing down on the block, then this force wouldn't necessarily be the same, right? So it's just like, as a stylistic thing, I like being careful about that and just being like, well, it's a normal force that happens to be equal to the force of gravity on the block. So, all right, so 4 points there. Free body diagrams are a nice, convenient 3 or 4 points. All right, let's think about how to find the final velocity. I did notice on I think Leo's paper, we are right now reviewing kinematics and forces, so we're going to do it that way. You can look at this, and I do think it's easier to look at it as a conservation of momentum question. That you can be like, oh, I've got the mass of the block times my initial velocity, and then later they'll like be moving together. That is a way you can do it, and you know, let's just solve that real quick so that we get a final number, and then we're going to do it the other way and prove that you can do it. So this gives us a final velocity, by the way, if you do it this way, of about 0.57 meters per second. We're going to get that in another way. So let's think about the other way we could do that. We decided that the slab. I don't know, which one do you want to talk about first, the block or the slab? I don't really care. Let's talk about the block. Let's talk about the block. The block is slowing down because of kinetic friction, right? So we know that for the block, right, I'm going to keep using red here, mu times the normal force, which will be mbg, is going to be equal mb times its acceleration, a little f equals ma. And so I can find the acceleration there is going to be mu times g. And given my mu, it's 0.2. That's going to be an acceleration of 2 meters per second square. I'm just going to take g equal to 10. If I think about velocity, right, what's happening to the speed of the block?
Increase.
Well, it's constant acceleration. We don't actually need to integrate, but what's happening to the speed of the block? It's decreasing. If we think about our kinematics equations, we do have a kinematics equation that tells us how speed changes over time. It's the first one. So we could say that the velocity of the block, it starts out at 4 meters per second minus 2 t, right? Initial velocity minus or plus acceleration times time. I'm writing negative here because it's slowing down, right? The acceleration's in the negative direction. For my slab, right? What force is pushing my slab forward? Yeah, friction. I want you to notice. Do I have to recalculate my friction force? No. It's the same force. It's the exact same force. You have to be really careful. What people want to do is they want to recalculate this and be like, oh, this is going to be mu times the normal force, and look at that normal force. The normal force here, it's the friction between the two blocks. The normal force is the force between the two blocks. I guess more to the point, Newton's third law, those two friction forces have to be the same. If you actually go and calculate what this is, 0.2 times 0.5 times 10, you find that this friction force is exactly 1 Newton. So if you go over to our slab, I've got a 1 Newton force that's accelerating the slab. It's going to get an acceleration of 0.3333333 meters per second squared, right? The two forces, the two friction forces have to be the same. Now, the slab is starting out at a velocity of 0, and it is speeding up, right? So it's 0 plus 1/3 t. Okay, it wants to know, it wants them to find identical speeds. So what am I going to do with those two things? How do I know when the speeds are the same?
Accelerate the slab and decelerate the block.
Yeah, until they are equal. So what am I going to do with those two equations? Set them equal to each other. Set them equal to each other. I'm going to ask, hey, when is 4 minus 2t equal to 1/3 t? And of course, you can solve this by hand, or I guess if you really wanted to, you could stick it in Desmos. That'll be 7/3 t. So t is going to be 12/7 seconds. That's not what they wanted. They didn't want the t. They wanted the final velocity. So what do I do with that t?
Plug it in the 1/3.
Yeah, I can plug it in either one because they should have the same velocity. I'm going to go ahead and plug it in the velocity of the slab just because that's easier. So 1/3 of that, the final velocity for the slab should be 4/7. And wouldn't you know it, 4/7 is 0.57 meters per second. So I do think you would probably prefer to do it the conservation of momentum way, but it is possible to do with forces and kinematics as well. Suppose this one is definitely kinematic. Suppose I wanted to know the distance the slab has traveled at the moment it reaches VF. This is, spoiler alert, a kinematics question. Which kinematics equation do I want to use? Okay. I could actually use the second or the third because I have time and I have acceleration at this point, but I do like the third one. I do like the third one. The nice one thing is it starts out at an initial velocity of 0. So I can just do 2 times the acceleration times delta x. And I know all of my numbers in there except for I know all my numbers in there. So 2 times 1/3. Is that right? Did I do that right? Nope, I didn't do that right. Oh, I did do that right. 4/7 squared. I guess I did that right. So I get a delta x of 0.49 meters or something.
I got it.
Yeah. If you use 9.8, I think you get exactly half a meter, which is kind of fun. But yeah, it's important. You need to, by the way, you do need to figure out the distance the slab travels. The block travels further than the slab because it like starts out at one end of the slab and then moves. It actually moves a little farther than the slab does. So you can't treat that. All right. So this is a little bit funky just looking at the rubric. This is like a 7-point question. If you do it the way we did it, there's like a couple points for finding like basically all the work you have to do to find the 2 accelerations is like 5 points because you have to like correctly set up all of the free body diagrams and all the things. A point for setting the 2 velocities equal to each other and then finding the final velocity, and then a point for the correct answer. By the way, anytime they say calculate, you have to give units. Like always be given units, even if you're not sure what those units are. Better to give a unit. And then 2 points for just choosing a kinematics equation that works. You can use the second one because you also have the time. But yeah, all right. So 9 points there. Last but not least, the work done by friction. How could I figure out the work done by friction on the slab? I could try force times distance. That is certainly true. That is certainly true. I could do that. It turns out there's a little bit of an easier way because all that work done by friction, where did it go? What did the work done by friction do? Yeah, it all turned into 1/2 mv squared. Do we know the mass of the slab? Do we know the final velocity of the slab? Which side of that equation seems easier to calculate? Yeah. So you could do force times distance. It does work. I mean, at this point in the question, you know the force and you know the distance it moved. Or you know the other side of the equation, but I happen to like the other side of the equation, which is going to be 1/2 times 3 kilograms times, yeah, like whatever. That was like 4/7 meters per second squared. And so you get about 1/2 joule if you do it that way. Yeah, you get about point. It's actually literally the same number as it's literally the same number as C. Like,
1 times.
yeah, it's coincidentally, even though they're different quantities, it is coincidentally the exact same number, which is kind of funny. All right. And as it turns out, that's 15 points. That was a whole FRQ. That was a whole FRQ. So that's going to bring us to the end here. I apologize that we don't have the physical packets. I'm going to go check with Copy Plus and figure out where they're coming from. But by next week, we should certainly have them. We'll meet up next week again and talk about energy and momentum. We'll have some more practice questions and another fun FRQ, or maybe we'll do one of the practice FRQs that's in the packet, because there are a couple practice FRQs that are in the packet. But we'll have these. There are lots and lots of FRQs that are publicly available online. You can go find them if you need more examples. But yeah, thank you.
Good on, saying it.